Welcome to the third workshop on the series of AI development in the EOSC. Today we had the workshop about federated learning in the EOSC. Just a reminder, this is part of the whole series in total of 6 different workshops. So we had already the general platform introduction, as well as points about image processing with AI4EOSC. And also, please remember that the recordings of these meetings are and will be available online. Just a reminder, AI4EOSC had recently released there was a first release. So this is the new toolbox for developing running artificial intelligence models in the European Open Science Cloud. And this is now available for new users. Just another short announcement. So we had also proposed open call for new use cases. Basically, in the project, we had already few, and now we are opening to the wider base of also other applications. And we want to help accelerate the development in the EOSC. So if you are interested, just scan this QR code. The call is open till end of this month. Okay, sorry. Okay, so there is also the open symposium that you can vote for our session if you are going there. So this is the session on unleashing synergies for fair AI development in the EOSC. So if you think this is an interesting session, please vote on it. So basically today we will have 4 very interesting presentations. This will be, we have 4 invited speakers. So first we go through basic of federated learning, then we'll describe some threats in federated learning, then we will show one of the framework, that is Flower. And in the end, we will show Flower in the AI4EOSC platform demonstration. So basically, our first speaker will be Kadia Alibabei. She has a PhD in mathematics from the University of Porto, Portugal, and won the prize for the best doctoral thesis in mathematics and computer science fields. She earned her second PhD in industrial engineering, focusing on the application on the AI in the agriculture sector. And she works as a data analytics access and application specialist at the Karlsruhe Institute of Technology, Germany. And without further delay, I would like to ask Kadia to start the presentation in a moment. And so this is just a reminder that like during previous workshops, if you would like to ask any questions that will be asked at the end of each talk, please, you can scan the code, go to Slido, or scan the code here, and you can ask online the questions, and then we will ask the presenters at the end of each of the talk. So thank you very much for that, and we move to first presenter. So Kadia, the floor is yours.
Can you see my slide?
Yes.
Hi everyone. Good afternoon. Thank you, Marcin, for the presenting me. It's my pleasure to be here and talk about the basic of the federated learning. As we know, machine learning, especially deep learning, has revolutionized many fields such as natural language processing and image analysis across, and with data playing an important role in driving this algorithm. Centralized learning in machine learning refers to the traditional approach where all the data is gathered and stored in a central server to train a machine learning model. This process involves collecting and combining data from multiple resources into a single data set before training the model. But nowadays, we know that edge devices and Internet of Things devices generates vast amount of data, and gathering of this data in one place may pose various challenges such as data flow management, scalability, communication overhead, because of the intense competition between industry. They are not willing to share their data. And most importantly, data privacy. We need to make sure that we are compliant with strict data protection regulations such as GDPR and the new regulation EU AI Act. To address these challenges, federated learning comes into play. Federated learning was introduced by Google in 2017. In the first definition of federated learning, a central server coordinates the federated learning process. The server initializes the global model weights and sends them to the client devices. The devices then start training the model using their own data and send back the update model weights to the server. The server aggregates these weights using some aggregation algorithm and update the global model weights, and then sends the new weights back to the local devices. This process continues for several runs until the model achieves optimal weights or it achieves the maximum runs. One example of using federated learning in a real world is Google already use federated learning in Gboard in Android. When Gboard suggests a query, your phone stores context and your interaction locally on your device. Then federated learning use this data to improve the Gboard suggestion. Another example is that Apple has already employed federated learning to improve Siri's voice recognition ability while maintaining your data private. In the medical application, the federated learning was used to predict oxygen requirement for COVID-19 patient in the ER using chest X-ray and health record of the patients. Federated learning is divided into different categories based on data distribution, architecture, and learning model. Based on the data distribution, federated learning can be divided into cross devices or cross silos. In the cross devices, the model is decentralized across the edge devices and is trained using the local data on these devices. In cross silos, the client are typically a smaller number of organizations, institute, or other data silos like a hospital working together to predict the outcome of patients without sharing the data of the patient with each other. Based on the architecture, federated learning can be categorized into the centralized federated learning and decentralized federated learning. In the centralized federated learning is the initial definition. There is a server that could coordinate the training and do the aggregation of the local weights and send these new weights to the local devices. In the decentralized federated learning, the communication is peer-to-peer and is used when the client, the server is not trusted or is not reliable. Based on the learning model, federated learning can be categorized into horizontal federated learning, which each party has the same feature space but different data sample, and in the vertical and the other categories is vertical federated learning, where each party share the same samples or user while holding different features. In this type, we mostly talk about horizontal federated learning. A workflow in federated learning refers to the sequence of steps involved in the training and updating of a machine learning model across multiple decentralized devices. There are different workflows that we can use in the federated learning setting. The first one is scatter and gather that I already explained about it. Global model parameters are distributed to the client devices for local training, and then updated parameters are gathered and sent back to the server for aggregation. We also have cyclic learning that the server select a subset of clients. Training is done following a predetermined sequential order set by the server. Cyclic learning can be used in the centralized manner or decentralized manner. If it's centralized federated learning, the last client sent the model back to the server, and server broadcast the model to all the participants. But if it's the decentralized learning, the last client is responsible to broadcast the model to all the participants. We also have swarm learning, which is a decentralized subset of federated learning, where orchestration and aggregation is performed by the client. With swarm learning, training is done in multiple runs. In each run, an aggregator client is randomly chosen from all the clients, and then all training clients perform the training task on the current global model parameter. When they finish the local training, all the clients send their training result to the aggregator client, and that client do the aggregation and send the global model back to all the participants. In the traditional distributed learning concept, it's often assumed that the data on the different nodes originate from the same distribution and have a similar size. However, in the real world scenario, and especially in federated learning, data may be unbalanced and non-independent and non-identically distributed. To solve this non-IID nature of the data in the federated learning, several aggregation algorithms are developed. The simplest one is a federated average. Is a federated average. The local weights are collected and gathered again after training, after local training using a weighted average. Then we have fed products, which add regularization terms to the local loss function to penalize the local weights of client deviating from the global model. We have federated optimization, which is an extension of federated average, and instead of using just weighted average, it uses an optimization algorithm to update the global model weights. We have a scaffold, which add correction terms to the network parameters during local training by calculating the difference between the global parameters and local parameters. And we have DITO, which is a method for federated learning that improves fairness by personalizing the model. That means after some runs, one personal model is initialized with the global model weight, and it's trained on the local data of the client, and it's safe for that client. So in DITO, we have a global model and we have a personal model for each client. As we mentioned in the definition of the federated learning, the data remains on the local devices, but while the model weights are shared with the server. However, this alone doesn't guarantee the privacy in the federated learning. There are still some issues that need to be addressed. For example, some possible issue with federated learning is reconstruction attack to the terrain model. That means the original training data sample can be reconstructed from the model weights, or membership tracing. That means to check if a given data point belongs to a training data set, or when a participant whose local data has a certain property join the collaborative training. Here we have some examples from these two papers. The first one, they could reconstruct the original training data. The first image is from the validation set, and the middle and the last one are the reconstruction of this original image from the different version of ResNet using gradient of the model. And in the second one, they could trace when a participant whose local data has a certain property join to the federated learning training. In this case, this participant joined to the training after 250 runs. There are some solutions to avoid this issue with the privacy in federated learning. The first one is data anonymization, which is a technique to hide or remove sensitive attributes such as personality identifiable information. But this method doesn't guarantee privacy. For example, in 2008, Netflix started a competition named Netflix Prize, and the teams should create an algorithm to predict how people rate a movie. To help this competition, Netflix create a data set, and they remove the name of the users and replace some rating with the random rating. But these two data scientists from the University of Texas published a paper, and they had successfully identified the user names by combining the data set from Netflix with with ranking of the IMDb. We have differential privacy, which provide a formal definition of privacy by introducing noise to the query responses to prevent the disclosure of sensitive data. I have one toy example of this differential privacy here. Suppose that we want to collect a survey if people use the drug or not. After a user responds to this survey, we toss a coin, and if it's head, we send the real answer of the user to the server. If it's tail, we toss the coin again, and we send. If it's head, we send yes to the server, and if it's tail, we send no. So we cannot be sure if the response of the user to this question is the real one or comes from the noise. In the real world application, we use more complex method like Laplace noise addition or exponential mechanism. We also have secure multi-party computation, which is a cryptographic technique that enables multi-party to jointly compute a function over their private data. For example, we have additive secret sharing. Here again, one toy example is that suppose 3 employees wants to calculate the average of their salary, but they don't want to really reveal their salary to each other. In this case, say Anna has a 100K salary, and this 100 is split into the 3 randomly generated pieces, or called secret share. In this case, 50, 30, and 20. Anna keeps one of these secret share for herself and sends others to the other employee. The same for George and Caroline. Then they calculate the sum of this secret share and send this sum to the server. Server calculate the average of this secret share, and the average of this secret share is exactly the same as average of the real data. Then we have secure model aggregation, which is the same way as secure multi-party computation. But instead of working on the data, we mask the weights of the model, and we send this masked model to the server, and server do the aggregation on these masked models. We also have homomorphic encryption, which is a cryptographic method that allows computation to be performed on the encrypted data without decrypting. There are 3 methods for homomorphic encryption. Fully homomorphic encryption that allows to perform any number of operations, so is computationally expensive. We have somewhat homomorphic encryption that limits the number of operations that can be performed on the encrypted data, and we have a partially homomorphic encryption that allows only one type of operation to be performed, but any number of types. I think you will hear more about this solution in the next time. Another possible attack to the to the model trained by the federated learning is during training of the model. Participant can manipulate the training of the process by introducing arbitrary update and potentially poisoning the global model. There are some solutions like model anomaly detection, but in this case, server can have should have access to the real update weights of the local models. But when we use secure model aggregation, this method is not useful anymore. There are several well-developed frameworks that have already implemented what we need for the federated learning. The first one is Flower, which is a flexible, easy to use, and easy understood open source federated learning framework. It is frame agnostic, meaning that nearly every machine learning model can be easily migrated to the federated learning, and it's well suited for research and study project. And I think you will hear more about the Flower in the third time. We have NVIDIA Feller, which is a business-ready framework developed by NVIDIA, and it supports a variety of models and is again frame agnostic. We have TensorFlow Federated, developed by Google, and which especially designed for compatibility with TensorFlow. And we have PySIF complement with PyGrid, developed by OpenMind. It's compatible with the popular deep learning framework like PyTorch and TensorFlow. We have Federated AI Technology Enabler, or FAT, which is again an open source federated learning platform developed by VBank's AI group. Is a business ready federated learning framework, and it comes with a large number of modules, and it has backbone again for TensorFlow and PyTorch. In conclusion, there are some key considerations before setting a federated learning process. We have to optimize our client selection by selecting customer based on data quality and their reliability. We need to select the best aggregation algorithm and consider scalability and accuracy of the algorithm. We need to investigate and select the best framework that meets our specific needs for our application. We need to make sure about security enhancement, and we need to make sure that framework provide us encryption, authentication, and privacy preserving technique. And we need to make sure that we are compliant with the data privacy regulation and ethical guidelines. There are some positive aspects in federated learning, like data minimization of data transferring, building a larger and more diverse data set, and in result we can train model, more general and global model, and it's possible to do international collaboration. But there are some considerable aspects that we need to consider in the federated learning, like security issue, like model poisoning, bias, and fairness. Some federated learning setting may facilitate bias toward some parties that has more data, and since we don't have access to the data, we cannot interpret the prediction of the model. That's all I wanted to talk about, and I listed some references in my slide that I use for my talk. Thank you for your attention, and if you have any question, please ask.
Dia, thank you for very interesting talk. And so I will show now maybe just again the QR code, just so people could ask the questions. So I will share now also the screen, so you can stop sharing for a moment. Okay, thank you. Okay, just a second. Okay. And okay, so again, you can go to Slido, or you can scan the code. So just again, besides main speaker here, Kadia, we have here behind the whole team, just to introduce where you will be asking the questions. There is Judith Science Pardo Diaz from AI4EOSC, also Valentin Kozlov and from KIT, and also me, Marcin Pucienik from PSNC. And basically, so stop sharing. I'm looking what are the questions. So let me have a look. Okay, so how is a global model trained in vertical federated learning when the features for each client are different?
Yeah, in the vertical federated learning, we don't train a global model, but instead we train a joint model. Each party train a model with their features, and then at the end, this train model for each client should be joined for the inference.
Okay, thank you. I'm looking for the next questions. So what is the difference between the aggregation algorithm you listed?
Sorry.
What is the difference between the aggregation algorithm you have listed?
The difference is depend on your data. If you have the data that is you are sure that your data is identically distribution, you can use the simplest algorithm like federated average. But if your data is non-identically distributed, it's better to go for more complex algorithm. For example, in a scaffold paper, they show that a scaffold is faster in terms of convergence to the optimal solution, and then compared to federated average and prox algorithm.
Okay, thank you for the response. Let me have a look if there is any further question. No, not for the moment. So thank you again for your presentation. Thank you. And okay, before we go to next speaker, I wanted just to also to mention that in the slide where you can post your questions, you can also provide us feedback to AI4EOSC, basically. And the feedback, there is a polls, and the poll you can give us feedback. What would you like to learn more about in upcoming events as well? So we are very, please help us shape also the next webinars. We can always include something that is of the importance for you. Okay, so we now move to Alberto Pedruso. So he obtained his PhD from Universidad de Vigo in 2019. Currently, he is a Margarita Salas researcher as Atlantic, working at the scientific manager of the European project Trumpet. And this project focuses on the application of privacy-enhancing technologies in federated learning. So it's my pleasure to invite you. So please, Alberto, the floor is yours. So you can start sharing. You can start your camera and also share the screen.
Yeah, thanks a lot for the nice presentation. Just 1 second. Are you seeing the slides now?
Yes, it's in full screen, so you can start, please.
Okay, great. So I start. So, well, I mean, many of the things I'm going to discuss in this presentation are going to be in some way like overlapping with the previous talk, but the perspective is going to be slightly different. Here, we are going to focus more on some specific examples. Probably we are going to be more pessimistic, just discussing the threats and not as much how you can solve them. We can discuss afterwards in the questions if you have how we could address all these different threats that we have there. So the first thing, if we want to understand the threats, the privacy threats that federated learning introduces, is to compare, or at least to compare with the normal workflow that you would have in a conventional machine learning task. And as all of you probably know, one of the first steps is to collect the data and to prepare the data to do a right training. So the data is nice and you can really extract some insights, some information from them. And then just train your favorite model, your favorite machine learning model, either a regression, neural networks, tuning the hyperparameters. And when everything is fine and you have your model trained, you can use it, you can deploy it so in such a way that others can make queries to this model and can just make use of it, and you can get some benefit of the model with some work you trained. Through the presentation, I'm going to simplify things a lot by just including some very simple examples, 3 examples, focusing in a medical scenario where you have some hospitals with some training data. This training data is related to patient data, and they have actually very simple attributes, just age and weight. So in the examples I'm going to consider through the presentation, we will have these very simple data sets with age and weight, some patients with some names there, a very simple model where they are going to estimate like a cardiovascular risk. So any coincidence with reality is just a simple random fact. This is not a real model at all, it's just for illustration purposes. And once you have your model, queries are just, okay, you just compute, you substitute your variables there with age and weight, and you have your cardiovascular risk. So this is the typical flow that you have in machine learning. And now one of the issues is that right now it's super important to have the nice data, good data, to really train and have a model which analyzes well from your data. So to do this, you need to have data from different sources usually. The conventional way of doing this is, okay, I mean, in the end, you have to collect all the data to send it to a third party maybe, but basically a party that must gather all this data to run the machine learning model. So here, if we want to apply some protection, if there is like an adversary inspecting things, well, you could protect the channels. So, okay, when you send the data to this third party, you can apply encryption, for example, but in the end, when you are training your algorithm, when you are training your machine learning model, you have to decrypt the information. So this implies that you could have a lot of problems. And this is exactly the point where federated learning appears. Because the objective now is in some way try to distribute this training in such a way that with this third party, what you exchange is not the data itself, but are just some updates, model updates, or even some local trained models from the different entities that hold some local data sets. As I told you, we have this example with some hospitals. These hospitals have some private data. They train the model. They obtain a local model update. They send this model update to the aggregator. The aggregator doesn't see the data, but only the updates, aggregates these updates, and this aggregation is sent back to the data owners, which now maybe the model is okay, or they would like to retrain again, and this process can continue till some convergence criteria is satisfied. One of the things I want to mention is that we are dealing here with a more specific case, which is a cross-silo setting. We are assuming that these hospitals have a reasonable amount of computational resources. And this already removes some of the possible threats that we could have, for example, in a cross-device setting, where maybe in each of these aggregation runs, some of these devices disappear, and you have to find ways to make that your model converges, even with in each run, you could have different devices connected and sending updates. Here, on the contrary, you could have maybe 20 data owners, and they are going to be there for the aggregation. They could really run the training algorithm. But there are different threats, let's say here, that are the ones we are going to discuss now. So now we go to the real topic of the presentation, which is privacy threats and attacks. So we have our example with these super nice local datasets in each hospital. And one of the issues we could have here is of the two typical questions that, for example, we are trying to address in the European Project Trumpet is a specific record, a specific person in the database? This could be one possible attack. One adversary tries to know this information by only inspecting these updates. Another one is, okay, I already know that this person or this record is in the database. I would like to infer one specific attribute. And there are other possible attacks that were also mentioned in the previous presentation, like poisoning. But these poisoning attacks could affect slightly more to the convergence on the model, not privacy itself. So we are going to focus on the two first here, which are more directly related to privacy issues. So I have here one example just to illustrate how the objective of these attacks. So you have an adversary, you have this local database in one of the hospitals. And for example, the aggregator could see one local update sent by the hospital. And from this local update, right now we know, like in the current literature is reported, that you could launch some specific attacks just by inspecting these model updates. You could ask the question of whether Alice is in the training database. This attack could work with some probability, with some effectiveness, but this is one possible attack, which is membership inference. And then you could have other type of attack where, okay, I would like to know the age, or I would like to know the weight of Alice. So usually when I talk about this, people really see that the second type of attack is a clear vulnerability, but the first one doesn't seem to be as relevant, because in the end, knowing that someone is in the database is that dangerous in terms of privacy? Well, the answer is that it is. I have an example just in the next slide, but I forgot I had this slide before the next one. So we will see it quite shortly. The point, and one of the things I wanted to highlight is that when you have this cross-silo setting with the aggregator coordinating the training with all the hospitals, the aggregator is a quite strong adversary in the sense that the aggregator can see all the local updates from all the data owners. So the aggregator is in some way the most dangerous party that you have in this setting. The data owners could also try to inspect information, but a priori the only information they see in all the runs is the aggregation. So in some way they are like some sort of weaker adversaries than the aggregator. So you are able to address the aggregator and you can apply this sort of solutions that you apply to the aggregator to the data owners. You should be more or less fine with that. So the aggregator should be the first party you should try to defend against. So the example I had to illustrate why membership inference is actually more dangerous than it seems, and I searched on the internet, so I'm not sure if this is true, but this is what I found on the internet, is like from people between 45 and 49 years old, you have a probability or the risk of having cancer, any type of cancer, is 350 per 100,000. And this is the general risk that you have. However, this is the a priori information that an adversary has. Okay, I know that any person in the world between this age has this risk of having cancer. However, usually when you train a machine learning model, the training data is balanced. So you have half of the people, if, for example, you have a classifier, which classifies on this person is going to have cancer, this person has cancer, this person doesn't have cancer. If you have a balanced training data, And if you have an adversary which is able to find out whether this record of this person is in the database, now as the data set is balanced, you already know that this person has a 50% of probability of having cancer, just by knowing that this person appears in the database. And this is, I think, is quite relevant, because this means that, okay, you're only leaking 1 bit. So the leakage in terms of information is 1 bit of leakage, but this bit of leakage totally changes the posterior probability of having cancer. So this is the privacy that you are losing. I think this is a relevant example that illustrates how you should take some care on how you manage these things. And now finally, we can start to go into different threats that can appear in the federated learning setting. So first, I will start with honest but curious, which are adversaries that are in some sense like gossip. They would like to know many things regarding the other data sets and the data of the hospitals, but they are going to follow the protocol. So for example, if one of the adversaries is the first hospital on the left, is going to train perfectly, is going to be a nice guy, but all the aggregated updates that is going to be receiving is going to try to know more information regarding the other datasets. And if the adversary is in this case the aggregator is going to do everything fine, it's going to aggregate, everything is going to fine, the model is going to work, but it's going to try to find out as much information as possible from the different local updates that the aggregator is receiving. And I have this sort of probably very silly game. I'm just trying to have some titles of different threats that could appear in this scenario. And one of the first things that we must consider is actually which is the channel of communication, the channels that we are using between the aggregator and the data owners. Because if the channel is party to party, then, okay, the data owners are seeing the aggregation, the aggregator is seeing the local updates and aggregation, but if it is an open channel, then everyone is seeing all the local updates. So this influences the amount of information, and the type of techniques that you must apply there change depending on what you really want and the assumptions that you want to have there. And then also you could have assumptions like the aggregator colludes with one of the data owners, while the aggregator already sees all the local updates. If the aggregator is colluding with one of the data owners, has access to all or to the whole dataset of this data owner, which could give a lot of information to run better attacks over these updates. So like some of the attacks reported in the literature actually require to have like a third dataset, which is in some sense with some different measures try to be or to represent in some way the dataset of the data owner you want to attack. So this is actually a huge amount of information for the aggregator to be able to more successfully run an attack over the local updates that is seen. You could also have like data owners colluding among them and also with the aggregator. And this is important because in this very simple example with only 3 data owners, we can already see that with only the probably super simple assumption that, I mean, it's reasonable that 2 data owners are going to collude, they already are able to inspect and to know the local update of the other data owner, and they can use their own data to try to launch attacks over the aggregation and the local update to see whether they can find out information of the patients of the first data owner, if the first data owner is the only one which is honest. So, as I told you, the most dangerous party here is the aggregator. And it's not everything is bad. I mean, oh my God, we introduced federated learning in order to solve some issues, and then federated learning is introduced as many privacy issues because of these updates, because you can run some attacks over them. The thing is that you, as it was discussed in previous presentation, you can incorporate many tools there to protect the information that the adversaries can see. And for example, in the case of the aggregator, you can run some sort of private aggregation in such a way that you were able to input your local update as a data owner, and the aggregator is able to aggregate without successfully extracting information from the input updates, and is able to compute to obtain a final output aggregation, which is going to be, depends on what you want, only be seen by the data owners or also the aggregator, depending on what are your needs. And which are the tools you could apply for this? So like one of the tools is, for example, homomorphic encryption. Homomorphic encryption by default allows you to work with encrypted data. So like data owners could encrypt the updates. The aggregator homomorphically operates and aggregates, and then data owners decrypt the aggregation. Or you could also incorporate differential privacy. which introduce a different type of trade-off because it's distorting a little bit utility, or it could distort. It depends in the specific data set you have and machine learning model. But also, you must know that if the adversary is the data owner, homomorphic encryption doesn't provide any type of super amazing protection, because the data owner is seeing the same information that was seen without any protection. The data owner is seeing the aggregation. So if the aggregation is leaking information of your patients, you must incorporate other types of techniques, and probably you must combine homomorphic encryption with differential privacy, or secure multi-party computation with differential privacy, in order to address the threats which arise from these two set of parties. So, okay, this was super fast. If you have questions with this, please ask at the end. But I would like to go into the more malicious setting, right, on the dark side, where now the parties not only are curious, they are not only gossiping information, but they will also be able to deviate from the protocol to try to increase the amount of information they can obtain, they can infer. So we are going to see how these threats could be, but like, for example, the first thing is, again, the same threats we had before are going to be repeated here. You could have a collusion, but now the collusion between the data owner and aggregator is like more dangerous, because now it implies that the data owner can send a specific update tailored to reveal a specific information of another data owner. Or the aggregator actually can do whatever he wants, not compute the right aggregation, and just compute, probably, if we're talking about neural networks and gradients, a gradient that goes in the opposite direction of what the aggregator suspects is the gradient caused by the specific patient that he wants to reveal in some way. So by cheating, by tricking how the convergence, how the training algorithm is going, maybe he could expose or make more clear that this specific patient is contributing to the training because it's modifying the gradients in this way to compensate the fact I'm doing. Again, this type of threats appear like open channel or secret party to party, and this is interesting because with secret party to party, you only see the output from the aggregator, but if you have open channels, then you can expect what the other data owner sent, and this gives some sort of redundancy, and you can verify whether the aggregator is really aggregating, because you can see what the other sent, and you can certify that the aggregator compute the right value in some way. Again, the data owners could also deviate from the protocol, so send like 3 key updates in order to this. Yeah, to move for the yeah, I just received something in the chat, but right now I cannot open it, so I will continue. I will finish soon. And after all these threats I have discussed, it seems, and one of the things we could consider is that it seems that the whole functionality is some sort like flaw. There are many issues there that we don't know how to really address. And so in order not to be so pessimistic, I just wanted to show you like 2 very simple solutions without even using pets that allow you to protect against this malicious behavior. So for example, in the case of the aggregator, in the end, what you need is to add redundancy. So for example, you could have several aggregators, and if you can assume that the majority of them are going to be honest, then it's perfect. You are removing the ones who are not really aggregating. So adding redundancy in many different ways is the possibility of removing this malicious behavior from the aggregator. And from the point of view of the data owners, they could try to cheat, and they could really manipulate the data they send in order to even not really privacy, but also to affect the convergence. And in this case, we could actually choose different aggregation rules that are more resistant to outliers in such a way that you can remove the effect or minimize the effect of these data owners that want to affect the convergence of the model. I actually include like one example, not really federated training, but federated statistics, because they are not computing a model, but actually just an average statistic. For the case, for example, of the age. So if you see here in this image and you see the age in all the data sets, if you compute the mean, the average, okay, it's 52, perfect. However, you compute the median, now it's 51. So in many cases for real data, the median and the mean are not going to be the same value. So you're not going to obtain maybe what you really want. However, if now one of the data owners is trying to cheat, and for example, sending something which is like absurd, like 200 for the age, you can see that the average is totally changing the value, now having like 98. However, if you use the median, you obtain again a 51, because the median is able to remove the effect of this data owner which is trying to cheat. So like these two examples, just adding redundancy to address the aggregator and just probably trying more robust aggregation rules, which are like in the literature, there are reported like probably quite a few, and a list of many aggregations, and actually with analysis of the convergence, the symptotic convergence of these different aggregation rules, is probably a nice way of addressing these different types of threats. On the other hand, if, for example, you use homomorphic encryption to provide privacy against the aggregator, the average is a function which is much easier to be computed than the median. The median, there are already papers trying to compute the median with homomorphic encryption, for example, but the median is a function which is much harder to compute homomorphically. So this gives already like some sort of trade-off. Like you could have the median, you can address this sort of dishonest data owners, but then protecting with some patch techniques the aggregation becomes much harder in some way. And this is really something that you must deal with your application and the operation that you need, the amount of data owners, and many more specific factors that could appear in your training. And now to conclude, we were talking about different privacy threats and some sort of, with many toy examples, just to illustrate how they appear there. But it doesn't make sense to say we are going to apply many patch techniques, we are going to make our architecture super robust, if you are not really able to say, this is the privacy that our implementation has. So actually, in the Trumpet project, what we are trying to do is to elaborate a set of privacy metrics tailored to the federated learning setting in such a way that you can really measure like some sort of thermometer, saying there is a high leakage here, and then you can decide, because the point is that sometimes you don't really need to apply patch. It could have happened that with the amount of data owners you have, and with some very simple protection mechanisms there, you already have enough privacy and you don't need to apply patch. So adding patch in this case could be just an overkill. You don't need that. However, in some other cases, because of the data you are using and the amount of data owners maybe is not very big, then you really need to apply, for example, differential privacy to increase privacy. And we need ways of measuring this privacy leakage. And this is actually something we are exploring right now in Trumpet. We were actually exploring different possibilities for this metric, and we have like developed like metrics in terms of measuring the success probability of some specific attacks, like for membership inference, for example, more related to differential privacy, measuring the privacy budget. But in the end, we want to have like a set of metrics which are complementary and can measure different types of threats, like the specific leakage of the state-of-the-art in attribute inference, the state-of-the-art in membership inference, like theoretical leakage in this aspect. And as I cannot include all the metrics that we are discussing in the project, I only include one of them, the one which is developed from my team, so probably advertising my team here. But it's just, for example, resorting to a metric related to the mutual information. So if you have a system with input X and output Y, and you compute the mutual information between X and Y, if both are modeled as random variables, actually the mutual information, what it's telling you is the uncertainty that remains about X when you know Y, which is perfect because it's what happens in federated learning. Your Y would be the updates that you are exchanging, and the X could be your training data or the specific features that you want to protect in your training data. So the mutual information is giving you the leakage on average that your training is producing through the whole training. So we're actually trying to produce metrics based on this mutual information, how to correctly compute the mutual information, because it's not easy, and to be able to do it actually in a reasonable time. So, for example, for the case of membership inference, if the Y represents the different updates that you are exchanging through all your epochs or your training epochs in aggregation runs, and this the other variable that you can see here represents a random variable of the membership to the dataset of a specific record, you could actually measure which is the risk that you have of leaking, that this specific record in your dataset is going to be leaked, the membership, when you exchange these specific updates. And actually what we realize is in the end, the problem reduces to how easy to distinguish two different distributions, like the probability density function of the updates that you are exchanging, but conditioned that the record is not in the dataset, and the same but conditioned to the fact that the records, or to the specific record, the target record, is in the dataset. So when the mean of these two distributions are far away, it seems that it's quite easy to attack, it's quite easy to distinguish the two distributions, and then you can say, okay, this record is in the database or not. However, if they are overlapping in some way, it's much harder. And this gives something interesting, because this tells in some way which is the most effective way to add noise, to distort your data in such a way that you can maximize utility and increase the security, the privacy, such a way that, okay, we are not going to add just random noise to all the updates. We are going to add noise in such a way that we minimize the amount of noise needed to have this difficulty on distinguishing the two distributions. And that's all regarding this part, just as a conclusions. And I'm 25, and they told me that I have to finish in 25, so I'm going to be super fast in the conclusions. I have tried to show like some aspects of federated learning with some probably very simple and examples, showing that although it's quite interesting and introduces some benefits, it also has some relevant security and privacy challenges that we can actually address in many ways with the use of more robust architectures or other different changes in the protocol that you are doing, but also incorporating PETs like secure multi-party computation, homomorphic encryption, differential privacy, even zero-knowledge proofs that I didn't say, but to force honest behaviors by the participants. And this is not enough, because if you start to apply PET technologies without really knowing which is the privacy that your implementation has, maybe it's just killing with a cannon mosquitoes, because your implementation with the specific data that you're doing is okay and has enough privacy guarantees. So you really need to incorporate like complementary privacy metrics that are able to give you like an idea of which is the privacy leakage that you have and which are the PETs that you must incorporate for your specific use case. And that's all. Thank you for inviting me.
Roberto, thank you very much for this very good, very detailed presentation on. So I think it was very interesting. So let me have a look on. So please, to all our to the audience, you can ask questions through Slido. So let me have a look on the questions. Basically, how could HA be applied in FLR architecture, since each client will have its own public and private keys?
So the question is, how do you use homomorphic encryption with different public and secret keys, right? So usually when you say that you apply homomorphic encryption, what people don't say is that if you trivially apply homomorphic encryption only works with one public and one secret key. So data owners must use the same public and secret key to encrypt and to decrypt. And this implies that either you must introduce a new party into your architecture, which is in charge of only decrypting, or you must assume that the data owners are not able to see the updates because they are encrypted with the same key and all of them know the secret key. So this is an issue. Homomorphic encryption already by itself introduces some problems in the architecture. The solution, because there is a solution, is something which is called like adding multiple keys into homomorphic encryption, which is multi-key homomorphic encryption, which allows to combine ciphertext with different keys. And when you decrypt, the final aggregation depends on the keys of all the data owners. You must engage all the data owners in some sort of protocol, some sort of decryption protocol. And in this way, they can recover the information. There are other approaches, like it's called threshold homomorphic encryption, where in the beginning, there is a setup phase where all the data owners like sending the keys. They engage in some sort of protocol, and they are able to, with an encryption scheme, where they don't know the secret key of this scheme, but they know that the secret key depends on their own secret keys. So they can encrypt, nobody can decrypt, and the only way of decrypting is when all the data owners participate. But this already simplifies that you cannot solve the issue with only homomorphic encryption, because in some way you are combining homomorphic encryption with other techniques, like which come from secure multi-party computation, like secret sharing and something similar. I try to be fast in the answer, sorry.
Okay, thank you. Let me have a look if there is another question. There is one, how can privacy metrics be incorporated into FL pipeline, and how might they be combined with other pets?
Yeah, this is maybe already discussed through the presentation. The point is that each data owner should be able, before sending the update, to apply some sort of a set of privacy metrics to evaluate how much these updates are leaking about its own local data. And if everything is fine, okay, now I share my update. Or if it is not fine, maybe it should apply differential privacy, or I should distort the data. But it should have some sort of traffic lights telling green, red, in such a way that you can decide. One of the issues is that this privacy metric maybe is not easy to compute and could have like a computational cost which is similar to the local training that is already doing. And it's something that, for example, we are exploring in the project, and it's not really easy to answer. And there are a lot of research to be done there. But this should be the process in which it is applied, or should be applied.
Thank you, Alberto. So
Yeah.
thank you again. I don't see any other questions coming for the moment.
Okay.
So thank you very much. And we will move, so you can stop sharing the screen. We will move to next presenter, that is Javier Fernandez Marquez. He's a research scientist at Flower Labs. He works on the core framework and develops the Flower simulation engine, which allows to run federated learning workloads in a resource-aware manner and scale these to thousands of active clients. So basically, his interests lie in the intersection of machine learning and systems, and basically more concretely on running on-device machine learning workloads. That is a key component in federated learning. So he has got his PhD in computer science from University of Oxford. So without further delay, Javier, the floor is yours.
Okay, thank you very much for the introduction, Martin. So yeah, today I'm going to be basically presenting Flower, which is a framework, in my opinion, the best framework to do anything related to federated learning or federated analytics. And I'll start by giving a brief overview about how federated learning works, just in case you joined just now to the workshop. Most of these concepts have already been mentioned earlier by other presenters like Alberto and Fahime, but without further ado, let's go into it. So one of the key ideas, or the way I like to summarize federated learning, is that FL moves the training to the data, instead of you having to move all the data to where the training takes place, which is what happens in centralized training. And I'm going to show you how the typical federated learning pipeline looks like. And it is comprised usually of just 5 steps. So first, you have your model, your global model that lives in the server. And this is a model that it might be pre-trained or it might not. And you want to federate the learning of this model. Usually, the first step involves sampling some clients. These clients can be anything, can be smartphones, can be IoT devices deployed, in the countryside, in a factory. It can be big servers in hospitals or financial institutions. It doesn't matter. The process is always roughly the same. So you sample a few of them. They receive a copy of the global model. So all the clients generally receive the same model, and then they start doing local training, each with their own data. And because each of these models have been trained with different data partitions, they look different after the local training has been completed. Once the local training is finished, each of these clients or nodes or participants upload their model to the server again, where all these updates get aggregated. As we have seen in previous talks, there are multiple ways of aggregating the model, but one of the most common ways, and probably one of the first aggregation strategies you want to start with, is called Fed average. And just completing this loop of 5 stages is what we usually refer to as a round in federated learning. And how many rounds you do is one of the big hyperparameters in FL, and it very much depends on things like the complexity of your task, how many clients there are, and many other factors. So that's roughly how federated learning works, like at least the 101 of federated learning. And as we have seen from previous talks, FL, you can generally categorize it into 3 big different categories. Cross-device, where the training takes place, are usually IoT devices or smart devices like smartphones, smart speakers, and so on. They enable a wide range of applications to be personalized to your particular use case or your particular self. Cross-silo FL is more targeted, is more envisioned for organizations or institutions that want to collaborate and train a model. For example, hospitals is one of the most prominent examples in this domain, but there are many more. Not only hospitals are interested in collaborations. And finally, one that I like to call intra-organization federated learning, which means that there can be big companies, big multinational companies that they own all the data, so they could perfectly send it to a centralized location in terms of ownership of the data, but because of maybe different legislations in different countries or different regions in the world, moving this data is actually not feasible or is a big problem. Sometimes it's not because of legal challenges, but it's because moving big volumes of data can be quite difficult in itself. So federated learning is a solution for all these type of machine learning settings. So that was all I wanted to share about federated learning as what it is. What the remaining of this talk is going to be is about Flower. As you probably you already know, and it has already been mentioned in this workshop, Flower is, I think, the best federated learning framework. At least that's what the community seems to be agreeing on. Flower has a super rich federated learning developer ecosystem with many contributors, and they are really helping shaping how Flower looks like and how it is evolving. Many of them have been contributing in many different ways, maybe with just examples, helping add some functionality to the core framework, adding baselines, and more. And what we see is that in Flower, this rich community, there are a lot of interactions over Slack, over GitHub as well, and more recently on Discuss. So we recently launched discuss.flower.ai, which we think is one of the most ideal places to ask questions. For example, if you are starting with FL, you can do the same on Slack, but Discuss is purposely designed for this type of interactions, which we think is going to make things even easier for users, starting with Flower. And Flower also is used to build the latest research. I'm talking research that is published in top-tier venues like NeurIPS, ICLR, ICML, and computer vision conferences. One of the evidences that Flower is really useful for doing all type of research is one of our initiatives that put together all the big list of Flower baselines that you can find on our website, and you can run or modify to your particular use case, or even use a baseline to develop a better baseline with a new algorithm, for example. Let's take a look at what the Flower framework is, and then soon after that, I'm going to show you how you can start by writing a simple server and client FL application using Flower. So if the Flower framework is short definition is as a unified approach for federated learning, analytics, and evaluation. And many times when we present this simple sentence, people might ask questions like, does it support, smartphones, or is only for Python, or can I use C++? Can I do cross-silo, cross-device? Is it only for horizontal FL, or can it do vertical? Does it integrate with some of the privacy-enhancing technologies like secure aggregation of VP? And the answer to all this is yes, you can make use of all these flavors of federated learning and use all these privacy-enhancing technologies. And I will talk about that a bit more later. Because Flower is framework agnostic, this means that you can very much use it with the same tools you are used to work before you were doing federated learning, for example. Maybe you were super excited about Keras, about PyTorch. Well, you can develop your server and client applications using these tools. Maybe you are more a data scientist, not so much doing machine learning itself, but you can still use scikit-learn and other frameworks like maybe XGBoost. And of course, you can wrap everything with integrations like weight and biases that will help you to analyze how your experiments are going. And you can wrap your client application inside an Android app or an iOS app as well. We have examples for all this in our website. And one of the biggest strengths of Flower is that it allows you to work on your federated learning project all the way through the development of this project. You can start running your client and server applications on your laptop or your workstation. Once you are happy with how things are interacting with each other, you can take the exact same client and exact same server applications and do a large-scale simulation, maybe using a multi-GPU server that you have at your disposal, maybe in your university or at your workplace. You can scale up these simulations to do multi-node simulations very easily. Sometimes simulations are great when you want to, for example, find the right hyperparameters for your application, or you want to understand how a particular aspect of your algorithm will behave under certain situations. Like, for example, you want to develop a new custom aggregation algorithm, or you want to test out how your particular setup will behave if clients suddenly drop. So you can simulate all this in simulation super easily with Flower. When you are approaching deployment, you could perform simulations on for example, on a farm of IoT devices, like a farm of Raspberry Pis, or you can even mix simulations in the sense of having a high-performance server running alongside some Raspberry Pis. And one of the reasons why you would want to do this is because while simulation, in the sense of pure Python or pure C++ simulations, is great for test different ideas at the software level, let's say, sometimes you want to make some hardware level decisions based on things like metrics power consumption of your devices, for example, or you want to regulate how your federated learning application works based on network congestion, for example. And all these things, you can still have a simulation, but if you can run it on real devices that are easy to control, that's even better. And then, as I was saying at the beginning, all this, the same application you develop in Flower, the same client, the same strategy, you can directly take those files and use them in your deployment to do, what we call a fleet of devices wherever they are. They don't have to be in the same. They don't have to be collocated in the same region. Okay, so with that fast introduction about what Flower really offers you, let's take a quick look at how the code looks like. And I'm going to here start as making no assumptions on whether you are already familiar with Flower or not. But as I go through the slides, I will be adding a bit more and more content. And I hope that towards the end, you will learn something that you didn't know about Flower, even if you are already like a regular user. So the Flower API is quite lightweight. And as I said earlier, it's framework agnostic. So you will see that there is no PyTorch, there is no TensorFlow in the core part of the framework. And to start with Flower, usually you will start with a server.py and a client.py. As server looks, a fully functioning server looks as minimal as what you see here on the left. It requires you just to specify an aggregation strategy, for example, Fedaverage, but Flower, you have over 20 strategies you can choose from. And then the only thing you will need to do is to start your server. And you can specify as well certain configurations for this server, like in which IP and port is it going to be running. And then specify a configuration, like for how many rounds do we want to do federated learning. I want to highlight that this method of starting the server with flower.server.start server is something we are moving away from. It still works, but later in the slides, I will show you what's the preferred way of running your server. Then if we look at to the right, we have a client. This is the skeleton of how Flower clients most often than not look like. At least this is how I always work. And you will see that there are 4 methods. And if I talk about them briefly in order, so get parameters is a method that it can be called by the server to fetch the parameters that are on the client. Set parameters does basically the opposite. You pass it some parameters, and those parameters will be applied to the local model on the client. Feed is often where the majority of the logic and the majority of the work takes place. Feed essentially means it requires you to define what's the training loop that the client is going to do. The client is going to execute once it receives the parameters from the server. We'll see an example of how that looks like. And then the idea would be that in the feed, you train the model locally, and then you return it to the server. Similarly, with evaluate, it has an identical signature to feed, but the idea is that you won't train the model. You would just evaluate it on the global validation set, for example. If we look at now this client.py file with everything there populated, and we zoom in into some parts, like for example the constructor, we'll see that this is nothing special. So for example, here what I'm doing is I just instantiate my model. This could be anything, could be as simple as an NLP, or it could be as complex as an LLM. And then you just need to load what the local dataset of this client is. For example, here I have another function, a utility function that will bring me the training set and the test set, which is like a local validation set. If we now zoom in into the fit method, you will see that the first thing I do is with the parameters that are being sent from the server, I just call the set parameter methods that will apply those parameters into the model that this client has. And then the thing I will do is I will be just calling another function called train. This is entirely up to you to implement. It doesn't have to be called train. But one of the key things I want to highlight is that this training function is no different from the typical training function you are already very familiar with when you do centralized training. In fact, you could take any training code that you can find in other tutorials like out there, like maybe PyTorch or anything, that are not specifically designed for FL. You could take that training code, put it here, and everything would work. So it is entirely up to you, because to the client's eyes, the client thinks it is doing a centralized training. And then once this local training step has finished, what the client has to do is to return the parameters to the server so they can be aggregated. And similarly, we can make this, even though the server I showed here is fully working, we can also add a bit more customization to the server side. For example, you can specify more, you can further specify what are the hyperparameters of your strategies. Different strategies support different hyperparameters. Here, for example, I'm saying, oh, I want my Fed average strategy to only sample half of the clients, but I want a minimum of 10, for example. And this, what it would do is the server will wait until at least 10 clients are connected, and then it will randomly sample half of them. And this is, for example, one of the minimal examples in Flower. You can find something very similar to this in our GitHub as one of the quick start examples. And this was like a brief overview of a simple federated learning client and server using Flower. Because here we have, I believe, in the core researchers and engineers, I want to give a bit of a deeper look into some aspects. I'm not going to go into a lot of details because I see I'm already kind of running out of time. And what I want to talk about is the strategies. The strategies is really the brain of federated learning rounds in Flower, and it allows you to do pretty much anything you want to do. For example, here I'm highlighting some parts like if you want to change how the sampling of client works, instead of making it random, you want to bias this sampling for any particular purpose, you can do it. Maybe you want to customize how the models sent from the clients are aggregated. You can do it in Flower as well. Maybe you want to modify how frequent certain stages in federated learning, how frequent they are executed. For example, the global evaluation of your model, it might be very time consuming, so you can also modify its periodicity, or you can change it completely. You can do that in Flower as well. Flower, what I've shown so far is the way Flower has been working for a while, and it has really been amazing, the kind of projects and papers that people have been, and projects overall that people have been putting together. What I'm going to show you now is a brief overview of how Flower is going to be working. It's already working, and how it is going to be working in the future, that is going to make things even more versatile. So in the same way that we had the server and the client, which is what I was showing to you a few slides ago, now we are transitioning into something that we call, and the server and the client were talking together, talking to each other directly. That's how Flower has been working for a long time. But now we are transitioning to a different model where the server is no longer called the server, but we prefer to call it the server app. You will see that now we are not calling start server, but what we are creating is just an object that is a server app object. I'm going to make it just small here so we need a bit of space. And similarly, the client is not going to be the client anymore. We're going to create a client app. And if you have been paying attention, you will see that the core part of the code, like the strategy here, the configuration, and in terms of the client structure, it hasn't changed in any way. The only thing we modify is that we are not going to launch the server app directly. We are not going to launch the client app directly. With server app and client app, we have almost all the ingredients to run the updated version of Flower, but we need two more. One is what we call the super node, which you can think of it as a long-running process that will execute client apps. And then there is something in between that we call the superlink, which is essentially a relay that relays messages sent by the server to the supernode and back. So now there is not a direct connection between supernodes and server apps. Everything goes to the superlink. And we think that this really is going to bring a lot of versatility and robustness to your federated learning projects. One of the key benefits here as well is that, for example, let's say you have a collaborator that wants to develop a new server app, but you want it to run also on the same clients, let's say. Well, you don't need to shut down everything. This collaborator of yours can start the server app, and it will run on the existing clients, for example, if the permissions allow for that. And you can see that we can take this even further, and then while before one client was tied to one Flower client object and one application, as a result, now we can have multiple nodes can run multiple applications at once. So to learn more about this, what we often label it as Flower Next, I would recommend you can either look into some of the examples that have already been transformed in this way, or you can watch the keynote that Daniel gave at the Flower Summit just last month in London. I'm not entirely sure how much time I have left, but I will continue. Please, Martin, whenever I have only 5 minutes left, let me know. So talking about examples, I'm a big believer in that learning by example is very powerful. And in Flower, we have over 30 examples. What I want to show you next is not so much about how to use different aspects of Flower, but I want to show you that really you can federate almost anything. For example, you can take the any model of the latest family of state-of-the-art vision models that are called vision transformers. You can also run them on Flower directly, and you can federate, for example, you can federate everything, the full training of these models, or you can federate the fine-tuning of these models. This is what we do in this example, VID fine-tune. It runs with Flower simulation, and one of the key benefits is that you can, for example, parallelize multiple clients on the same GPU if you have a big GPU. For example, here I was running it on my 3090, and I was able to fit 5 clients running in parallel. Not everything is about vision, even though a lot of research in federated learning is about vision. You can also federate a classification of voice commands. For example, what we did here, we took OpenAI's Whisper model, and what we fine-tuned was the last layer that helped us to federate the training of detecting words like yes, no, up, down, and so on. We made it and this is particularly important because if you want to train a voice assistant, for example, you don't want to collect voice commands from people from different households or different places where the voice assistants are used. Why? Primarily because of privacy reasons. I think this is also very well connected to what Fahimed was presenting earlier about Siri. So you can find an example in Flower in the GitHub repo showing how to federate the fine-tuning of a Whisper model, and this runs on Raspberry Pis. And finally, of course, because of now LLMs seem to be everywhere, you can also train LLMs using Flower, and you can fine-tune them as well. If you are a bit tight on GPU budget, probably you want to give it a go to fine-tuning first. There is an example of that in Flower, and I'm finishing very soon. I don't have time to talk about Flower datasets, but Flower datasets and the partition of datasets is one of the main challenges to address when you are doing research in federated learning. So you have a big dataset, you want to partition it. Well, if we make the partitioning very easy, you can focus all your energy in developing a better aggregation strategy, for example. So with Flower datasets, we make the partitioning really trivial. And we have a big selection of partitioners that you can use. Popular ones like the Leeds-led partitioner, for example. Yeah, this is almost everything I wanted to share. You can find all the information in our website, flower.ai, with many more resources, including blog posts. You can read about the latest things we are up to in Flower. Everything's on GitHub. We have our YouTube channel as well. And that's it. I'm happy to take any questions.
Javier, thank you so much for this presentation. So it's very exciting. So let me have a look on the questions that we had from audience. Okay, the first question is, the Flower server can be used with example TensorFlow clients or NVIDIA Flare clients? That's the first question.
So the first, you can what is the first type of client? You mentioned pure TensorFlow or
TensorFlows.
Yeah, you can use TensorFlow with PyTorch, TensorFlow with Flower, either on the client side or on the server side or both. So that's for sure, yeah, a big yes. In terms of NVIDIA Flare, we had a big announcement last month in the Flower Summit where we are starting a collaboration. There are some details on our blog post, and there will be some here. I recommend you to reading that. There will be some bigger updates in a few weeks from now.
Hey, thank you for this reply. Let's move to second question. Does Flower support the use of pets such as differential privacy?
Yes. So with the recent change to Flower, the thing I was talking about, like that is called like Flower Next, we call it like that for now. We make it super easy to plug in things like differential privacy and secure aggregation. There are in fact 2 examples in Flower showing how to do that, DP and secure aggregation together. So yes, it is definitely possible. I think you're muted.
Okay, sorry. Is Flower compatible with other FL frameworks? That's I see probably the last question.
Yeah, so I think this is partially related to the first question, I believe. So we are working. There is a ongoing collaboration with NVIDIA Flare team and Flower. We are starting some form of integration, and we'll have more to share about this fairly soon. Yeah.
Okay, so I think that was the last question. So thank you very much for your presentation. Very appreciated.
Thank you very much. Thank you.
And you can stop sharing the screen, and we will move now to Judith Sainz-Pardo-Diaz. She's a researcher at the Advanced Computing and E-Science Group at the Spanish National Research Council. She's a mathematician with a major in computer science from the University of Cantabria and master in data science from the Universidad Internacional Menéndez Pelayo. She's developing her PhD thesis in privacy preserving techniques in data science environments. And yes, Judith, the floor is yours. And please start the presentation. Thank you very much.
Thank you. Thank you very much, Martin. Thank you very much for the introduction. And thank you very much to my colleagues, Fahime, Alberto, and Javier for their wonderful presentations. And last but not least, thank you very much on behalf of all the AI4EOSC consortium to all the people who have joined this third webinar. So, well, my name is Judith Sainz-Pardo, and in this last session, my plan is to make a demo on how can we perform a federated learning training within the AI4EOSC platform. And as we have already seen in detail, the architecture, the high-level architecture of a federated learning training, and we have already seen also how can we move from the centralized machine learning to the distributed or federated learning to federated learning, machine learning or deep learning models. I want to start by explaining a little bit the AI4EOSC high-level architecture that we have already saw in the last meeting, not but in the first webinar that we had in this series. You can check the high-level architecture of the platform in the interactive C4 diagrams that are openly available, and you can scan the code and check it in detail. But also we have summarized it in this slide, where I'm just going to focus on this part of the architecture. First, we have the development environment, and we can use the AI4EOSC platform with Visual Studio Code or with JupyterLab. And this is quite important because, for example, let's think about a federated learning settings. Probably the clients will need to explore their data before starting the process, and they can use the platform for that. They can maybe ask for resources such as CPUs, GPUs, memory, etc. And they may use Visual Studio Code or JupyterLab. Or even if they wish, they can just run a deployment using Visual Studio Code and then use a plugin for JupyterLab for better visualization. And in the federated learning side, we are deploying the federated learning server using Flower, and Javier has already explained us a lot of the details about Flower. So that's just for you to know how we can perform the federated learning in AI4EOSC, what tools are we using for this purpose, but also for the high-level architecture of the platform. So I'm going to focus on services for AI or machine learning or deep learning development in the platform, and focusing only in this case in federated learning, as you know. So as we have already explained it, we want to provide users with federated learning tools because it's quite important when we are building machine learning or deep learning models to provide users with the capability of performing it collaboratively and decentralize it, because in some cases, we may not be able to centralize a data set, maybe due to technical restrictions, but also in a lot of cases, as we have already commented in the last talks, for example, in medical imaging, when we are dealing with hospitals who want to collaborate, we have also privacy restrictions on our data. And for that purpose, it's quite important to provide users with these kind of tools which allow them to perform this kind of training in a collaborative way, in a decentralized way, using this kind of distributed machine learning approaches with a focus on the privacy. Our idea in AI4EOSC is to provide users with the management of the experiments through the platform with the dashboard, which is quite intuitive, as we are going to see, and is quite user-friendly. So it will make users easier to perform their experiments and to manage them. Also, we aim to allow the users to perform their federated learning training with their clients or data owners. We can say clients or data owners, but I mean the same with these two terms. But the clients can be started both from the AI4EOSC platform, but also, for example, users can start their clients with their local computers or even with using their own cloud platforms or from external cloud providers. I mean, for example, in some cases, it may be quite interesting that the users will run the code for their clients for their local computers, because if they have some technical or privacy restrictions, they will not probably be able to upload their data to the platform or even to our storage management system, which is Nextcloud. They will want to work with their data locally, which is one of the main concerns in federated learning. So with AI4EOSC, we provide users the ability of deploy the server within the platform in a quite simple way, and then run the clients from their local computers or their own cloud systems. So I want to present an advantage that we have implemented in the AI4EOSC platform when dealing with a federated learning setting. And we were quite interested in providing users with an authentication system. And with an authentication system, I mean that in some cases, when we are performing this kind of learning task, the clients and the servers may need to be authenticated, because, for example, if I'm working from the server side, I may be able to see that some client is sending to the server some updates to the model that are misleading, for example, due to mislabeled data and so on. And maybe I would want to remove that client from the training. So we have provided in this platform with a system that allow only 2 authenticated clients to connect with the server. And this is important because in the simplest configuration of the federated learning server that we had in the AI4EOSC platform, the clients only need to enter the deployment ID where the server is deployed, and they just join the federated learning training. And this is quite intuitive because when we are working in a simple federated learning server, in a simple federated learning setting, when we deploy the server, we take the ID in which the server is deployed, and then the client just need to connect to such ID. But we want to perform a further step in which the clients need to enter the ID, in this case, the deployment ID, but also a token for authenticating with the server. And in order to do so, we have performed an authentication system using tokens. We call it tokens, but you can call it passwords or as you wish. In order to the clients need to enter that token prior to their incorporation to the federated learning training. So in order to do so, we have used Vault from HashiCorp as our secret management system. I'm going to show it later. And then the federated learning server will retrieve a list of authorized tokens for client authentication from Vault and will check the token provided by the clients. So in case the client provided the server with an unauthorized token, then the client will not be able to connect with the server. The connection will be refused. In addition, the users can be able to manage the tokens, to add new tokens, to revoke older tokens. For example, here in this screenshot, you can see how we have a list of secrets in which we have the secret for the client number 1, for the client number 2, and for the client number 3. But we can remove any of them or create new ones. For example, if we find that the client number one is an untrusted client, which is using mislabeled data, or which is performing a kind of intentionally or unintentionally poisoning attacks, we can just revoke this secret, and this client will not be able to connect anymore to the server using this token. Of course, we can create a new token if needed for that client or for others. In order to perform this authentication system, we have implemented some extensions to the Flower library that work alongside with Vault. And I'm going to talk about this later, but you can check the code, which is, of course, openly available. So first, we have some extensions for working with Vault, and then some modifications to the Flower library. We have modified a little bit the Flower library in order to be able to introduce the credentials, the tokens, for authenticating the connection. And for this demo that I want you to see within the AI4EOSC platform, I'm going to use some data available openly and which are widely known. Again, we came back to the case of, let's simulate that our clients are hospitals, again with medical images, as the other speakers has already talked about. But in this case, our goal will be to classify chest X-ray images according to whether or not the patient has or not pneumonia. So as we had a centralized dataset for this example, we divide the initial training data into 3 different clients, simulating, of course, again, 3 hospitals that want to collaborate, want to build a global model, but of course they are dealing with sensitive data because this data is related to different patients, and they will not probably be able to centralize their data. So we divide the initial training data into 3 clients, as you can see in this slide here, and we perform an stratified train test split and create a quite simple model for this demo. It's a quite simple multi-layer convolutional network that we have implemented using Keras. And to make a real example, we have also created the 3 clients. We have distributed the data related with these 3 simulated clients. We have distributed it to 3 different instances in the Institute of Physics of Cantabria cloud. So this data is now allocated in our own cloud. You can see here that there are different IP addresses for the different clients, and we are going to perform the training really distributed within 3 different cloud instances. And now I'm going to move to the AI4EOSC platform to see this working live. So here you have the dashboard of the platform, which is quite intuitive. We have first the modules. For example, we have modules concerning plant species classifier. We can take this kind of module, which are pre-trained, and perform, for example, transfer learning, but we're interested in the tools. So in the tools, we have here the Federated Learning server, which is a server deployed using Flower. So first, I need to log in the server, and in order to do so, I use the EGI check-in, but there are different options for login. And now we start the Federated Learning server. Our first step is concerning the general configuration, which is quite simple. I'm going to put a deployment title, for example, demo webinar for this one, and the description, just for us to do not forget what we wanted to do here, which is a demo for chest X-ray prediction of pneumonia. Well, we have then the service to run. We always recommend to use Jupyter Lab or Visual Studio Code, because with Federated server, as you can see in the documentation, you can check all this documentation to know more about the Federated server. But broadly speaking, with the Fed server, you will not be able to monitor, to change anything within the server, just to monitor the process, but not, for example, if you decide to change, let's say, the number of rounds, you will not be able with the Fed server, but you will be able to do so using Jupyter Lab or using Visual Studio Code. So then we put a password to our deployments, and then here, this is quite important, we have the Docker tags. And if we want to use the Federated Learning server without the authentication part that I have explained, we can select the tag latest. But if we want to have the possibility of authenticating the clients, we need to select the Docker tag tokens. So our next step now is hardware configuration. This is not quite important because In this case, we are creating the server, and the server will be in charge of aggregating the models that are received. We will need probably more computational capability from the client side. For example, we may need for GPUs or more CPUs, but for the server side, this hardware configuration will be enough in this case. And last, but of course not least, because I think that is the most important part, is the federated configuration. And this is one of the strongest points of using the federated learning server from AI4EOSC. This is the way in which you can configure your federated learning server without entering in code details and so on. You just need to select here the number of rounds, the evaluation metric. Of course, you can enter more than one, and we have here some predefined one of the most classicals. The minimal number of clients. In this case, we have 3 clients. I'm going to keep 5 rounds, which is quite a small value, but just for this demo. And we have several aggregation strategies implemented. Some of them already explained by Fahime in the first talk. So when we are ready, of course, we can show help and get some tips regarding all these federated options. But when we are ready, we just need to submit this module. And while this is ongoing, I'm going to connect to the different clients that we had. So here's the client number 1, client number 2, and client number 3. So that you can be able to see that we have deployed the different clients in 3 different machines. So this is really distributed in 3 different machines and with the server deployed in the AI4EOSC platform. So this is ready. The server is running now, and we can go to the info of the deployment where we can start open it in the deployment ID that we have already created. For example, in this case, we have select Jupyter Lab, but the most important part here is to keep the deployment ID, because we need the deployment ID to be able to connect the clients with the server, and also the part concerning the tokens. As I already explained it, in this case, I selected the Docker tag tokens because we wanted to be able to authenticate the clients with the server. So as we have 3 clients, I'm going to create 3 different tokens. We can create it quite simple from this interface within the dashboard, but we can also use the Vault interface that I can show you also here. This is the interface of Vault, and we can go to secrets, to users, to deployments, and if we go to the dashboard, we can take a look to our deployment ID, and here we have it, and here we have the different secrets that I have just created for this example. Here we can take a look to the tokens that are created. So this is from the server side, from the AI4EOSC server side, and we can just enter into the code details. Again, as I have already explained it, deploying using Jupyter. So here we have the code, and we can take a look to the README, in which we have some general information on how to get started, but it's quite simple. So we just need to open a terminal, and we enter into the folder Fed server, and then we just need to run, and you can see it here, the file server.py. This file has been created when we have created the federated configuration, so we do not need to change anything. This is quite ready to use. I can close it. But of course, if in any case we want to change it, because let's suppose that I introduce 5 as the number of rounds, and now I change my mind and I say, okay, I want to perform 50 rounds. Then I can enter in this code and change it for example, in this case here, federated rounds. Then I will just need to change it here. But we are ready to start the federated learning server. But first, let's take a look to the clients and configure the clients. And I'm going to show you the case for the client number 1, because the other 2 are just the same. And first, we need to provide the token. This is an old token that I that I had for a backup in just in case. And if I go here, we have the client 1 token. Of course, we can, this is just metadata, so we can take any other token. And now we just need to enter this authorized token in this code concerning the client number 1. We have here the data from this client. We load, we process the data. Then we define this simple convolutional network model created using Keras. And then I'm not going to explain so much about how to create a Flower client, because I think that Javier has already explained it quite well previously. But in this case, this is a quite simple client, Flower client, in which first we have the function getParameters, in which we use this model.getWeights, which is a function from, in this case, TensorFlow. Then we have the fit function, in which we first put the parameters, the weights. For example, in the second round, we will need to update these weights with the aggregated parameters, and then we fit. Here, of course, we can change number of epochs, batch size, and so on. And we return the model weights and the number of data used for training. This is important, for example, if we want to perform a federated average aggregation strategy. And finally, we have the evaluate function, in which, again, we put the weights to the model, and then we just use the evaluate function from TensorFlow, for example. So then, in order to connect with the server, as I already explained it, we have developed different extensions. One of them is what we have called AI4Flower, as you can see here, in which we use this function bearer token auth plugin to introduce the token. And then we can just start the server because we have just give the token. So we need also to introduce the deployment ID to know to which federated server we want to connect. So let's take it, which is here in the information. We have the deployment ID. So I just copy paste this ID here, which is the deployment ID in the AI4EOSC platform. And then we just need to use the function start client from Flower. And in this function, we just need to enter the server address given by the deployment ID, the client, the Flower client that we have previously defined, here root certificates, and last but not least, in this case of authentication, the call credentials part, in which we use this auth plugin. So in these lines of code, we have defined the part both for starting the server using the authentication. So we are ready for the side of this first client. So let me activate the virtual environment and start the server to see this in progress. So I'm now in the AI4EOSC platform. So from the server side, I can start the code of the server. And if you have already worked with Flower, this will seem a little bit different, but it is just because of the configuration of Vault, in which we get, okay, we are getting the tokens and we are configuring the tokens and so on. So now the server is ready is requesting initial parameters from one random client. So then we can just run our first client. And then we will need to do the same with the other two clients. So from the client side, we can see that the connectivity is ready. So if we move to the server side, we can see here that now the federated learning process is starting. However, as we introduce 3 as the minimal number of clients, it will not be starting until we have 3 clients connected. So let's quite quickly configure the other 2 clients. So let's go with client number 2. And the configuration is mainly the same. The code is mainly the same. We only change the data. So first we enter an authorized token. So again, I go here to manage the secrets and I copy paste the token for client number 2. And again, we read the data, we create the same model as for client number 1. We define the Flower client, and here we perform the same configuration. We need to introduce the deployment ID that again can be found in the deployment information. And we are ready to start the second client in the same way that the first one. So we start this one, and I'm going to start with the third one so that we are ready. Again, this client, the second client is also ready, so let's go with the third one. And same configuration than in the previous one. We change first the token. So we move to the platform, we copy paste the token related to client number 3. And then same configuration. We read the data for client number 3, we define the model, we define the Flower client, and last, we need to enter the deployment ID and use the start client function from Flower. So let's again copy the deployment ID. And now we are ready to run the third client. So now the third client are ready, and we can see here that the first epoch is starting and the training is starting in the 3 clients that we have running for this example here. So if I go now to the server side, we can see that it has changed from FL starting to feed round number 1, sampled in 3 clients out of 3. So we have received the information from these first 3 clients, but now we can different clients can join to the training if they have an authorized token. Of course, if I create a new client, for example, client number 4, I can also use one of these tokens. Can be used more than once, but we can create a new one, client 4 token, but we cannot create another token, for example, client number 1, because secret names must be unique. For example, if now from the server side, I see that client number 1 is sending data which is quite strange, not data, but updates to the model, then I can just delete this secret and this client will be removed from the training. So now we just need to wait until the 5 rounds finish for these from the server side, but also from the client side, we can see the evolution in terms of the number of rounds of the training, and we are now in round number 2. We can take a look to round number 1, where we receive 3 results and 0 failures. And while we wait to this to finish, I wanted just to show you some results that we can get for this example here. In a setup that I created this morning, these were the results obtained, both for the loss, for the accuracy, and for the area under the curve. And here we have some example of this curve, in which, of course, we had quite good results because it's a simulated sample. This is quite far from reality in a real medical image classification process. But we can see that with the federated learning approach in this example here, we get quite interesting results. And also, you can check this article that we published, I think that the end of 2022 or at the beginning of 2023, I'm not sure, in which we analyzed the performance, but also the scalability of federated learning when we have different amount of clients. For example, here, we compare the centralized approach with the federated learning approach with this client, with this amount of clients, with 3 clients, but also with 10 clients. You have here the code if you want to check it. And in this work, we also check it out. How can we proceed in case we have intermittent clients? I mean, some clients leave the training and some clients join the training. So let's take a look to the code, and we are now in round number 3, but I'm going to, as I think that I'm running out of time, I'm going to the conclusions, and then we can see the demo finished. And we have seen that a complete federated learning training can be performed using the AI4EOSC platform, and this is quite friendly for the users that are not familiarized with federated learning, because they can just start the server from the dashboard using the intuitive interface, and this is quite simple using Visual Studio Code or Jupyter Lab, just interactive with the platform interface within the dashboard. Also, we have seen how can we create the clients, and the clients can be created first, of course, in the AI4EOSC platform. If you need resources and you can upload your data to the platform, then in most cases that probably will not be possible due to technical, but probably due to privacy restrictions. You can upload your data and ask for resources and run your client code from the platform, but also you can run it from other cloud providers, locally from your computers, and so on. Then for the part of the authentication, we have created some extensions to the Flower library. You can find it in this repository here in AI4OS, AI4Flower in the branch develop, and also some modifications to the Flower library, which can be found in the AI4EOSC GitHub repository, in the Flower repository, and in the branch credentials. Also, the users can run the federated learning using tokens, as we have already seen this demo. And in order to do so, users need to use the Docker tag tokens. But if they do not want to use the authentication system because they simply do not need it, and in order to do not make users to deal with the tokens when they do not need it, they can use the Docker tag latest, and they will not need to use the tokens. And last, we have that we have used Vault, as which is from HashiCorp, as secret management system for allowing this authentication for allowing only the authenticating clients to connect with the server. And after going with the questions, I just want to show that the demo has the demo and the training that we were performing in the platform has just finished, and we get here some metrics. So first, the time in which the federated learning has finished, and we get some distributed results. First, we have here the loss, and here we have the loss in the round number 1, in round number 2, in the third one, fourth one, and in the last round. And we also have here the accuracy, which is increasing from round number 1 to round number 2. Here we can see a little decrease. Again, here in round number 4, it increases, and it decreases again in round number 5. But of course, this is a quite simulated example, so the results will vary very much in a real image processing from medical images setup. And just to finish, if we go to the server side, we have here the results for client number 1 with the federated learning model created, the accuracy, the area under the curve, and the loss for the test set, also for the client number 2 and for the client number 3. So that's all from my side. I wish that you have enjoyed the demo. And if you want to, of course, this will be recorded and you can check this demo when you wish. But also there is in our YouTube channel, in the AI4EOSC YouTube channel, there is another video with this same data, but without the token authentication, just in a quite straightforward way. How can we perform the federated learning training? So thank you very much. If you have any question.
Yeah, thank you, Edith, for this presentation and live demo. I think it was very impressive. Let me have a look on the questions from audience. How can I log in? May I ask for access to the platform?
Well, we can Martin, maybe put the introductory slides in which we talk about the open call for external users, but currently only authenticated users can log in into the platform. But we have opened a call with a special focus on federated learning. So if you are interested, of course, there is this open call, because we have received several petitions for joining the platform in these last weeks, but currently only authenticated users can log in. Yeah.
Yeah, if I can add on top, because it's the matter of the available resources. That's just that. So So we are opening for the new use cases, new users with this open call. But in general, we also discuss with all other initiatives that would like to contribute with their resources, but use AI4EOSC. In this case, we can open much more for other use case, if I can complement to your reply. So there are also other questions. So basically, once the FL server is deployed, is it possible to modify it? For example, change the aggregation function?
Yes, as I have already explained, for example, using JupyterLab or Visual Studio Code, you can just enter into the code details and change, for example, the number of rounds or the strategy if you change your mind. Yeah.
Thank you. Let me have a look on other questions. So once the server has been created, can more secrets be generated in case there are more clients than the minimum
Yes.
entered into configuration?
Yes, as I have I think that I saw it while I was finishing, but you can create as much secret as you need because maybe other clients want to enter the training and so on, or you revoke one secret and create a new one. So you can create as much secrets as you wish.
Okay, let me have a look. So 4, 3, 2, 1. So you have still chance to ask questions to Judith or any other speaker. Okay, so basically, just thank you, Judith. So I don't see any further questions. So thank you for your presentation. I will just show again one slide, okay, as a summary. So basically, just to remind the open call for new use cases, here you can scan the QR code and you can apply. So we are really very open for any kind of use cases, so and collaboration. And I think with that, we are finishing our third webinar. So we will soon announce the next webinar series, so our next 3 webinars. So this will be announced. I think we will do it next days with the announcement. So please stay tuned and please join us for the next webinars if you find it interested. So thank you for today's meeting, and we are closing, I think, in time.